But what do you do if you are interested in finding out how big an interval is? And so an interval could be, say, the distance from here, where we had, I think that was a 75, and here, where we had, it was a 120, 75 and a 120. Like, how do we find how big of an area under the curve that is? So if we want to find how much of the area under the curve falls in this red area, so all of that, how do we find how big that is, right? Well, I'm going to show you how to do that. So let's say that we want to know how much of the area falls between an x value, an x falls between 75 and 120. So that's how we can write an interval. So 75 to 120, and let me make this a bit darker for you. So how much of the area falls between 75 and 120? Well, there's a few ways that we can do this. But fundamentally, they all kind of revolve around this notion that first you would find the z-values for 75 and for 120. So you find the z-values for 75 and 120, and we just did that, so we know that the z-value, but to do that, you would use a z transformation. So you would convert your observations, your raw observations, if you will, you convert those into z-values. And once you do that, we know that in this instance, an xi equal to 75 is really negative 1.66 with this population that we've got. And we know that an xi of 120 is really equal to positive 1.33. And if you're really nitpicky, I suppose you'd pick 1.67, but let's in 1.33. Got these two z-values, and each of these values correspond to an area under the curve. So if we look at our z-table, the z-table that we use, this one right here, we know that if we have a 1.66, or a negative 1.66, we look it up on the z-table. So here I find, and it's going to be hard for you to see this, but you get the general idea. I read up, it starts with 0 down here, and as I move up, it moves towards negative 3.8. So I go, and I'm looking for negative 1.6, so negative 1.6 is here. And then I look for, so 1.66, it's really closer to 1.67, so let's pick 1.6. Well, screw it. Let's do 1.66 just for the sake of argument. On the exam, if you're off by a tiny bit, that's not going to kill you. So with that, we end up coming down to this particular place. And that gives us 0.0485. So this means that if this z-value here were negative 1.67, or actually, sorry, negative 1.66, that 0.0485 would lie to the left of that position. So 0.0485, or 4.85% of the area under the curve, lies to the left of that position. So we know that that is equivalent to 0.0485 of the area under the curve. And if we wanted to write this on here, we could say, we could put a P there for probability underneath this diagram, so P for probability, and we know that a 0, at a z-score of 0, that's where half, so 0.5, of all the area under the curve lies to the left of that point. If we were going to make, so we know that this is going to be a z-score of negative 1.67, where that 75 is. So right there, negative 1.66 is what I'm using. You could use negative 1.67, which would give you a slightly different value. And screw it, let's use negative 1.67, which gives us a slightly different value here, 0.0475. So in this situation, we're kind of damned if we do and damned if we don't. Either the value that we have is actually just beneath this or just above it, because we only have 2 decimal points. So negative 1.67 is what we have right here. Negative 1.67, and that corresponds to 0.0475, right? So this means that from this point over to this way, that we only find 0.0475, the area under the curve. So then what we need to do is go over here and figure out how big this area from the z-score of positive 1.33, how big that is all the way to negative infinity. And so the way we do that is we look at our z-table. This first page only tells us negative z-values. So those are values those correspond to observations that are smaller than the mean. But we actually have observations that are bigger than the mean. And so we need to find for 1.33. 0 starts up here on this side. So 0, so we get a 1.3, so positive 1.3, and then to get the 3, we go to this position up here. And what do we find? Lo and behold, 0.9082. So we find that this corresponds to 0.9082. 0.9082. And so the way that we can find that then is we just subtract this value from that value. The first step then is to find the z-values. The second is convert z-values to proportions, or areas under the curve. So that tells us, and that's what we just did there. And then the third is we subtract, at least in this example, subtract to find the actual interval. So subtract to find the actual interval. We have this big number, so 0.9082 minus 0.0475, and that gives us something. All you would really need to do on an exam is probably just draw your diagram like this and then do the subtraction. If you need to subtract, in some cases you won't. If you just needed to find this area here, then you have that, right? With this, then you end up with 0.8607. 8607. So we know now that this area in red that we originally were looking at corresponds to 0.8607 of the area under the curve. Remember, we got this by subtracting 0.9082 minus 0.0475. That gives us 0.8607. So we have this large area, we subtract the small area, and it gives us the size of this interval, right? Which is bounded by 75 centimeters on the lower bound and 120 centimeters on the upper bound. 75 centimeters corresponds to negative 1.67. We know that from what we had done just about 15 minutes ago. And then we know that 120 corresponds to positive 1.33. There it is. So that's how you determine how big an interval is. Right? So 3 steps. You find your z-values for the upper and the lower bound. And so you find these z-values using the z-transformation. You convert these z-values to some area under the curve using a z-table. So know how to use your z-table before you take the exam. And then you subtract the smaller value from the larger value to find the size of this actual interval. You subtract the area associated from the lower bound from the area associated with the upper bound, and that gives us this interval, like how much area that actually is. And that's how you determine how big an interval is.